So where we stopped, we spoke about the fact that we have to calculate the prefix average, and the objective of the prefix average is that we have 30 days or 40 days or a year of prices, and we want to calculate an average that basically adds up the next day's price on a daily basis. So if you were to do this, right, the easiest, the simplest way of doing this is to write two for loops. So the first loop that you will write will go from here. So this is your first loop. It will cover the first row, then cover the second row, then the third row, then the fourth row, then the fifth row, and so on and so forth. I'll call this the outer loop. And then within the outer loop, I will do another for loop. So this is loop 1, let's call this A. And then I'll do a second loop, and that loop would do what? It'll say, okay, if I'm in row 1, let's take the prices for row 1. So row 1 only has 133, divide it by 133 by 1, and that's the first one. So I can store that. Then I'd say, okay, now when I run it for the second row, I'm going to take the first 2 and then repeat this. And then for the third, I'm going to do this and then repeat all 3. Then for the fourth, I'm going to do this for the fifth. And the loop will basically run, the inner loop will run for as many times as there are number of rows. So from a programming perspective, what I really want to do is, this is what I want to do. The blue line that you see, this blue plot is the price on a day-by-day basis. And then this average price that you see, this is your daily average price. And our objective is to do what? Our objective is to calculate this daily average price, so we can use this as a benchmark with respect to where things are. And we're using the share price of Google as an example, but our primary application for this in the banking application that we work with is to calculate daily averages, so that we can identify and track if there is anything suspicious, is there anything anomalous that's happening that needs to be tracked and addressed. Okay, so far so good. What would the sequence of actions required to do this? So when I said, there are two loops, this is what I meant. For all prices, or for all rows in this specific instance, which right now are from 1 to 18, what do? Take the price. So take the first price, 133. So let's take 133 here, right? And then calculate the sum of price. So when the first time I run this, I will take 133 and I'll run these numbers for 133. And then when I come out, what will I do? I'll simply store in my first row. So let's say I create a separate array, and this is my array of averages. And in my first array, number 1 would be 133, right? That's the first one. So the loop has run, the outer loop has run once, and the inner loop has run once. And when it has run once, how many times it has run? Just run for one row. So now I move to the second row. My second row is number 2. I have the price 131. Now what do? In my inner loop will say starting from 0, 133 and 131. Add them together, which gives me 264. So take 264 and divide it by what? Divided by 2. Divided by 2, I get 132, and this becomes my second calculation. So now the outer loop has run twice, and my inner loop also has run twice. The first time it ran for one iteration, the next time it ran for 2 iterations. Now I have picked up the third price. The third price in the outer loop here is 133. I add it where? I add all 3 of them together. So I say, okay, take 1, 2, and 3. Take all 3 prices, add them together. It's 133, 131, and then 133 again. So that's 266, and then 366, and then 367, and then 397. So I end up with 397, and I divide 397. So this is 397. I divide this by what? I divide this by 3, and that gets me, let's say, 132.5, for example. So now the loop has run, outer loop has run 3 times, inner loop has run 3 times, but the inner loop has sort of run in its third iteration, it's gone through. Then I go to row number 4 and I repeat this process. Do you guys follow what's happening? I'm basically tracing the 2 loops, the outer loop and the inner loop in front of you. And what we're trying to do is trying to calculate the average so that we can generate this plot, the blue line and the gray line. That's the objective. So now the question that comes up is, how many times will this loop run? If you run the math, this would run 18 times, correct? But how many times would the inner loop run? So the first time it will run for 1 time, the second time it will run for 2 times, the third time it will run for 3 times, the fourth time it will run for 4 times, 5 times, 6 times, 8 times. So the inner loop will run 1 plus 2 plus 3 plus 4 all the way till about, on the 18th time it will run for about 18 times. Is this efficient or is this inefficient? It's inefficient. Why? Because there must be, you're making the same as in, the first time you run it for 3 times, you've done the average till here. But on the 18th time, you're going to still do the average all the way till here. So for example, here in the 17th loop, you've already calculated the average for the first 17 rows. In the 18th loop, you again recalculate the average all the way from. So there is no need for it to run, right? There must be a better way, a faster way, an easier way of doing the same calculations. And I think the reason why I wanted to show you this is I want to give you a sense of, a nested for loop sounds really cool. There are 2 loops. What could be better than a for loop within a for loop? 3 nested loops, right? A for loop within a for loop within a for loop. This sounds really interesting, sounds really cool, sounds like you're a very sophisticated programmer because you've really gotten the essence of using for loops. The challenge though is that it is, in this specific instance, in the instance of the one that we're looking at, there are certain variations where you may not have an option anything else but write a nested loop, but you should try and minimize that as much as possible. In this specific instance, there is, luckily, fortunately, a way. Is there a better way? Is there a faster way, more efficient way of doing this? And the answer is yes. So you can actually write an algorithm where you just use a single loop. Just use a single loop, a for loop. And in that for loop, what do? You go from 1 to 18. And in that 1 to 18, all you need to do is just run the loop from here to here. And then every time, store this value. So Google sum of price, in the first instance, is just the first value. In the second instance, it's the sum of the first 2, then the sum of the 3, then the 4th, then the 5th, then the 6th, then the 7th. And then when you're going through the sequence, all you need to do is just divide. As you calculate the sum of price, divide it by the row. So that'll give you your average. So you can do this in one single loop. How would you write this code? If I gave you a minute to write this code, how would you write this code? Do you want to try it? As in, this is the code that I wrote. I'm not very proud of it, but I wrote it to show you how code that is perfectly fine from a syntax perspective, from a logic perspective, can still be horrible from an efficiency perspective. And there are things that you can do to fix it. So what would you change? How would you fix it? Here's the challenge, right? The challenge is that it's 2 loops and you want to fix the 2 loops. Why? Because right now this would essentially run, because this is the first loop, this is the second loop, this will run n times, this will run n times, worst case. It's looking about n squared. So the Fibonacci one, we had 2 raised to the power n. Now we're talking about n raised to the power 2. And what we want to do is we want to see if we can turn this into linear time. You have to answer the efficiency question, you have to ask yourself, what is the base case? This is the framework, right? What is the base case? What is the first average? What's the next average? What is the relationship between the previous average and the next average? What is the difference? And how can we use this to make this more efficient? And here I think our primary objective is, again, to use the same framework that we'd used in both the iterative solutions and the recursive solution. There is a base case. Then there is some set of intermediate steps, and then there is a logic that describes and defines the relationships that we see here. These are students in prior sections who've solved this. So initialize sum of price, initialize your array of averages, and then for all rows from 1 to 18, price for current row is assigned the price, and then calculate sum of price. Sum of price, then average is the sum of price by the row, and then store the average. And that's more or less round about it. More variations. Here's what Ayan did. sum of price. So you see, this is common. We've taken key takeaway. What did we do? We went from here, we went from two loops, an outer loop and an inner loop, which gave us n square time to a single loop. And that single loop essentially moved all the calculations that we wanted in one specific loop, and by doing that we reduced one loop. This is a illustrative, contrived example. There are other examples where you will see that there is going to be a lot more work required to reduce two loops down to a single loop. What we've done is we've set the context. We gave you 4 examples: Fibonacci, n factorial, sum it all, and prefix average. With the first 3 examples, we walked through a recursive implementation and an iterative implementation. And while recursive implementations may not always be more inefficient, there's obviously some overhead, but they may not necessarily be more inefficient. The Fibonacci sequence is an example, an instance of a recursive implementation, which basically moves into what we call exponential time. And then we looked at the prefix average, where we looked at something which is in quadratic time, n squared, 2 loops. So general question, if 2 loops is n squared, what is 3 loops? Is that n cube? Respond with a yes or a no. If 2 loops is n squared, because the 2 loops will run, each loop will run n times, and we take n into n, so that gives us n squared. What about 3 loops? Is 3 loops n cubed? Is the answer yes or no? Proof of life check. What about 4 nested loops? So loop within a loop within a loop within a loop. Is that n4? N raised to the power of 4? Are nested loops good for efficiency or bad for efficiency? They're great for logic. They make for readable code. But are they good for logic or bad for logic? So are they good for efficiency or bad for efficiency? Can you think of an instance where a nested loop is required? Can you think of instances where nested loop may actually simplify? So you think about this. You don't have to answer the question now. You have to answer the question now, but think about this. Are there instances, are there exceptions, are there boundary conditions where a nested loop may actually be required? And we'll come back to this when we do a review session next week. We'll come back to it later, and we'll figure out if there is an answer to this question. Now, so coming back to our discussion on efficiency, I think the 2 pieces of, there we go, multi-dimensional matrices, that's right, Antonio. When you think in terms of efficiency, there are 2 dimensions, space and time. And so far in our discussion on growth of work in terms of complexity, we've focused on time. I think a similar discussion also applies to how much space do we need for implementing and executing on a solution. What we now want to do is we want to go out and discuss maybe how the work that we did initially in the first couple of weeks compares and relates to the work we're doing now. So if you remember the first 2 weeks of the Scrabble assignments, the first assignment was go out and do the design, the second assignment was go out and do word generation. And how efficient do you think your original word generation algorithm was? Where you went out, so you did 4 or 5 things, right? First you said, okay, take all the tiles. Then you said, take all the anchors. Then you said, take these 2 and use these to do what? Generate all possible combinations. So do combos. Then you said, validate. Then you said, place. So this was step number 1, this was step number 2, this was step number 3, this was step number 4. And when you did the word generation, you realized that your yield, the resultant valid words which were actually valid and included in the dictionary, your yield was very low. As low as, let's say, 2%. Which basically meant that 98% of the work you did here was wasted. Is that efficient or inefficient? So inefficient, right? And if that's inefficient, is there a better way or is there a faster way of doing this? So what we found later on was that there is a better way, and that better way was essentially not do word generation with tiles. That better way said that rather than using a full word generation attempt, it may be better for you to build what we call a try. And this is the fastest Scrabble program in the world. So what you see on the right hand side is a tree that you can use to search for the words. So if you have, let's say, A, and then you have multiple letters depending on how many of these letters you have. For example, you have A and X. So A and X together will give you X. And if you have an E, you can also do an X. You can also do an XL, XL. So you can do this also. There are variations that are possible depending on what your first two words are. And we found that this is a lot more efficient than our original model, which was, take the anchors, take the tiles, consider the special squares, consider the special tiles, and then go out and do the word generator, and then from the word generator validate the word, and then make the word, and then place it on the board, and then place the word, and then figure out whether it's a valid move or not, right? This, to our mind, was inefficient, and the try solved many of these problems that we would do in sequence. It made it possible for us to score this in parallel. And how did the try compared with the dog? There you go, that's the dog. So if you just go back to the previous slide, this clearly has more nodes. If you count the nodes, you'll find that this is about 112 nodes. It's the same sequence of words. The sequence of words is here. So what I've done is I've generated the try and the dog for this sequence of words. So it's just selected, not the full list, but just a selected list of words that start with the letter A. And I've put this here and gives me about 112 nodes. And my dog, this is my dog, this is about 52 words, 52 nodes. So this is even more efficient. So now, sometimes efficiency is not a function of code. Sometimes efficiency is not a function of your algorithm. Sometimes efficiency is a function of how we store data, how we represent data. And you have a representation of a dictionary, which is a list. It could be a book, it could be a try, or it could be a dog. And by working with that specific representation, it becomes possible for you to do what? For you to actually build a significantly more efficient solution that does the same 5 activities you were doing prior to discovering or working with this specific representation. It was taking you an enormous amount of time. So rather than doing those 5 activities in sequence, you can now do the same 5 activities in parallel. Efficiency is not just a function of code and algorithm. It is also a function of the model you use to represent not just information, but also data. Internal representation is a very strong, a very key concept that you have to remember. Sometimes it's the representation that drives the algorithm. Sometimes it's the algorithm that drives the representation. There is back and forth between the two, and our job as computer scientists is to understand this relationship, is to understand where should the lead come from. Should it come from representation or should it come from algorithms? So if I go back, the point that I'm trying to make is you've got your algorithm, which is essentially code. You've got your data, which is essentially what we call representation. This is how you represent it, right? Sometimes how you store data drives the algorithm. Sometimes the algorithm you use drives the representation. There is a back and forth between these two. So you can't look at this in isolation. You have to look at both the algo and the data and how you represent data internally. In Scrabble's case, both the tree and the dog, the try and the dog, the word graphs, the tree with words and the graph with words, make it simpler and easier for us to find an optimal solution, a valid move, a correct move, a high scoring move, much faster than our original algorithm design, which was essentially a brute force design.